Great. Hi, everybody. Welcome to the first papers session for the first joint conference on AI and musical creativity. I'm the session chair for this particular session. My name is Roisin Loughran. I'm particularly honoured to actually be chairing this particular session, as you will see from the programme that rather than going straight into the papers, we're going to take a few minutes to remember somebody very important to this community who we sadly lost during the year. Just last September, September the 13th, we lost Professor Bob Keller, who was an amazing character, amazing part of this community. And we just wanted to take a few moments to remember him with some of the people who knew him well. Bob was a professor of computer science at Harvey Mudd College in California for 29 years. And anyone who knew him from the conferences, particularly MUM, ICCC, CSMC, those are the ones I knew him from, let's say, knew that he was such an amazing person to have at your conference, because there was nothing passive about him. He was always so active. He was actively engaged in Q&A sessions, in panel discussions. He'd always be at the posters, and he'd always engage with new research and with new researchers. And it was wonderful to have someone like Bob with such a wealth of experience and knowledge to be so eager to pass it on and to share his knowledge and gain new knowledge from new people. It was very clear that he was very, very passionate about research. As we heard this morning in the opening session, this particular conference is an amalgamation of two different previous events, MUM and CSMC. And personally, I'd met Bob a few times at MUM in the last 5 years or so, and that's where I got to know him as such a great person to have at your conference. And the last installment of CSMC, which was in 2018, I was actually the host of that in Dublin. And I was very excited when the submissions came in, because it was a much smaller conference than what we have this week. But I was very excited to see Bob's name on a paper. And so that year, earlier in the summer, when I saw Bob at MUM in Salamanca, I believe it was, made a beeline for him to just check, are you coming over to Dublin? And I was delighted to find out that he was. And true to form, he performed in the concert. He brought his student who won Best Student Paper. He was just an amazing person to have there. And it was just great. I think many people here will know what a great addition he was to any event. And going forward, he will be sadly missed at this event and at all events to come, I believe. Now, as I say, I only met Bob a few times at conferences. So we have some people here today who knew him better as students and throughout their careers. So I'll pass you over now to Shlomo Dubnov, who knew Bob much better. Thank you.
So hi everybody, and thank you, Rosin, for the beautiful words you said. I knew Bob for I think over a decade as a colleague, and we got to meet in a forum that we organized in USC with Elaine Chu, tried to build something called the South California Computing and Music Group. And I've heard about him before, of course, and I was aware of some of his software. But that's kind of how we got introduced. And since then, because the distance is not too far, we actually met several times. And he would come with his students to UCSD, mostly over the summer. And we engaged in some discussions. He also gave some classes and meetings with graduate students. And he was always super engaged and very insightful and very deep knowledge of basically the theory, the musical theory that he translated to his work. We were engaged later through some other, academic organizing conferences, like in the context of MUM, as I organized a workshop in another conference. And last year he came to UCSD. He spent his year as an invited professor. It was his sabbatical as a researcher in the Qualcomm Institute. And this is where we got really into it, almost daily interaction. We would have him participate very actively in the research group meetings. He interacted with the computer music students, with the CS and EE students, I mean, that was really like a close encounter in the sense that he would be so insightful. He would like any subject that we would bring up, he would be really tremendously helpful. And maybe the last interaction that I had with him was in the concert last year um, in Mume, and before that we also had a concert where he performed with some guests that we had from IRCAM, where he did his live coding using his improviser grammar. What I would like maybe to do, not to take too much time, is also one of our students, graduate students who worked with him during the year, sent me a small note. So if I may kind of quickly read this from Nakul Tiruvillamala, and what he expresses is really, I think, touching. I mean, so I'm reading his note. One of the things that really stood out to me about Bob was his amazing range as a human being. He truly epitomized the notion of Renaissance man. He possessed a deep understanding of the abstract truth of the world, but he also had this uncanny ability to render these notions in practical and meaningful ways. One moment he'd be talking about Chomsky's grammatical hierarchies, and the next he'd be killing it on the blues. As someone with a broad range of interests myself, it was really inspiring for me to experience Bob's unbridled vigor towards life. Despite his many gifts, it was perhaps his humility that struck me the most. While serving as a visiting scholar at UCSD, he took many classes alongside the undergraduate and graduate community. One imagine that is cemented in my mind is of Bob copiously taking notes for whichever class session he was attending. There was not a bone of pretense in Bob's body, only the degree to learn and to improve, the desire to learn and improve. Whenever I think of Bob, I feel inspired by both his intellect and the way he carried himself. He's a true inspiration and is dearly missed. So I think, these are very it's like words coming from the heart, and I think we all share this sense and impression of Bob as a person, as a scholar, and basically as a human being that was so dearly involved in everything he did. So yeah, I would say, yeah, share every word, and he will be dearly missed. Thank you.
That was lovely, Shlomo. Thank you very much. Yeah, it's wonderful to have, as you say, former students speak so highly. It doesn't surprise me actually at all that some people who work so close with Bob think so highly of him. We also have John Gillick, who's also knew Bob well, I believe, and worked quite closely with him, who's got a few words to say as well. Thank you.
Thank you, and thank you, Shlomo. It's great to hear your experience with Bob. So yeah, I was just so saddened to hear the news about Bob's passing. I know he's going to be missed by so many friends and colleagues and students. So I'm actually a former student of his, and I just like to share a little bit about how Bob influenced me. So I met Bob back in the summer of 2008. That was just before my last year of college. At the time, I was feeling, I guess, a little bit lost as a college student. Officially, my major was in computer science, but I was actually just passionate about making music. That's really what I was excited about. And I wasn't really sure that I wanted to continue with computer science or whether I was maybe on the wrong path. Anyway, I had this idea that, well, maybe I could make use of my computer science training by writing a computer program that would help people write music or learn music. And so I thought maybe I was the first one to have this idea, although it turned out I was wrong. People have been doing this for a very long time. So I did a few Google searches and see if anyone else had done this before, and I found Bob Keller. He was running a summer research program for undergrads, working and had people working on his software called Improviser, where he was developing a lot of tools and features for jazz students, which he used in his own jazz class, which he taught along with computer science. So I sent him an email, and I remember that he actually responded right away, and it was encouraging. And I ended up moving out to Claremont, California, to spend a summer working with him. So I guess that was more than 12 years ago now. And here I am, I'm still working on the same type of thing. And to be honest, there's just no way that I would be in the career I'm in now without Bob's influence. And it wasn't just sort of the material things that he helped me with, like helping me publish my first paper or writing me recommendation letters to get into grad school, you know, a number of years later. It was also just the example that he set for me at a really like formative time. So I guess one of the main things I remember about Bob was that he really just cared about his students much more than he cared about his own ambitions or his own career. And you know, he didn't have to work with sort of a struggling, lost 21-year-old undergrad like I was. He could have been working with much more experienced people, maybe PhD students who had all the skills to help him sort of accomplish his goals. But he just seemed to really love seeing his students succeed in a way that I had never seen before, and it really stuck with me the way that he was, and you know, now a lot of years later, I still sort of try to model a lot of what he was like. So working with Bob that summer, we had a group of, I guess, 6 undergrads or so, and he just managed to create such a supportive environment where we all really felt like a team, even though we were doing kind of different things. We were all working somehow on his improviser software. But I don't think that we could have succeeded, you know, and sort of ended up finishing a project that we could publish and so on without the environment that he created, because yeah, we were just so inexperienced, and to be honest, it must have been really frustrating working with me at that time. Like I didn't know very much about what I was doing. I didn't know how to code very well. I didn't know how to be organized. I didn't know how to read a research paper. But somehow he just sort of, his kind of calm and humble demeanor just made us all really at ease, and that not only did it put us at ease, it just sort of helped us believe that we could do this, you know, this research work that was new to all of us. And I think a lot of us went on to do PhDs later on, and I'm not surprised, because that's just sort of the having been through that, we just sort of realized that, oh yeah, we can do this. And I didn't realize until, you know, later that how rare that was, and how lucky I was to have Bob been the first person to mentor me doing research. And so, yeah, I think what it comes down to is he was just incredibly humble for such a successful and smart and experienced person. And he didn't worry about his reputation. He just wanted to do what he was passionate about, and he really wanted to see his students succeed. So yeah, we stayed in touch, you know, from time to time over the years, and I'm very fortunate that I got to catch up with him last summer at MUME, and we talked for a long time, just sort of about life and about you know, he was still passionate about the same stuff, still working on improviser, and yeah, I didn't know that would be the last time I saw him, but I'm just very grateful that I did get to see him again, and lucky that I met him when I did, and that he was such a great influence for me. So I'm gonna continue to try to be like him and do the best I can to pass on sort of what he taught me and the example he set for me. So cheers to you, Bob.
Thank you, John. Some wonderful memories there of Bob. Something that struck me that was very likely, and you've just proven it to be true, is that he was just one of life's natural born teachers, I think, and just clearly, as you say, his students were so important to him, and helping other people and mentoring other people was clearly what it was all about for him. And that was evident from the first time you met him, really, and clearly it stayed with those of us who are lucky enough to have him as a mentor and a teacher. So I'm really, really, really humbled and delighted to hear two wonderful point of views there from about Bob. And as I say, yeah, he'll never be forgotten by this community, and we'll miss him for all of these installations. So now we have to get on and do some work, I suppose. Time is good for the moment. So to open the session, then I would like to call on Michael Cairn, who's going to present Troco generative algorithm using jazz theory. And yeah, so when you're ready, Michael.
Hello, Matthew, actually.
Sorry. I'm sorry.
No problem. All right, so yeah, and thank you to Rosine and Bob for chairing this session. So yes, I'll be presenting Troco, which is a generative songwriting algorithm that uses jazz music theory. So I'll begin with a little bit about the inspiration for Troco and what specifically I'm focusing on, give a brief overview of jazz theory, and then talk about how it is used in the Troco algorithm, give a short demonstration of possible implementation, and then talk a little bit about next steps. So at its very base, music is a form of storytelling. It's about this idea that something is set up that needs to be resolved, and over time, a listener can see how it plays out. And in this sequence, in this narrative arc, this idea of tension and release is key. And it's something that links all the elements of a generation or a piece of music together. And so the Troco algorithm is based on this idea of a tension and release narrative arc. It's a tension release oriented composer that's driven by a tension and release contour that the user inputs at the beginning of generation. So just a little bit about some of the inspiration and prior work in this area. This is a very incomplete overview, but there's a lot of machine learning around classical music, and some of Bob Keller's great work, among other things, was in machine learning based on jazz music. And on the other side, there's also a lot of algorithms based on classical music theory and everything in between machine learning and classical theory. And then in terms of actual inputs for the user or a user of an algorithm to specify the contents, the desired contents of a generation, we have things like the valence arousal plane, we have things like scariness, and there are already existing many tension-driven algorithms using classical theory, but the slightly less explored area that Troco focuses on is specifically a tension-driven algorithm based on jazz theory, which remains somewhat less explored than traditional classical music theory. So a little bit about why jazz theory. And at this point, I feel like I should address the fact that, as Mark Levine wisely stated in his Cornerstone Jazz Theory book, that there's no one single all-inclusive jazz theory, but that there's this kind of common thread of development, this common body of ideas that has evolved from the beginning of jazz. And these core ideas, while not, an absolute truth, there's a central body that can be generalized and abstracted. And generally, jazz theory is also really powerful because a few key concepts can analyze very complex structures, and there's not a lot of restrictions in your choices of state or choices of movement. And I also think it's worth noting that the basic jazz music framework, the basic jazz theory framework rather, can be also used to analyze and create a lot of current popular music styles. So the jazz music used in Troco specifically is based on the work of Mark Harrison and Mark Levine. They're two of the leading authors of books and ideas in contemporary jazz theory. A lot of their ideas were used in the Grove School of Music, which was a jazz school that used to be in California. Mark Harrison, the author of many central jazz theory books, has also applied his central theory framework to pop music, R&B music, and many other styles. So Troco, the first implementation of Troco focuses specifically on generating chords, and chords are abstracted in a very specific way in jazz theory. So for instance, here we have a C dominant ninth chord, and we split this into a root and a quality. So the root in this case is C, and the quality is 9 or dominant ninth chord. And together, this denotes the notes C, E, G, B flat, and D. And the fact that we can split any chord into a root and a quality enables the analysis in terms of a chord's function rather than the actual notes themselves, because chords with similar qualities tend to function in similar ways regardless of their root. And the other central part of Troco in general is, again, this idea of tension and release, the fact that there's over time built up rising stress that leads up to something. It's something that needs to be resolved, and then subsequently we release this, and there's a relaxation and a completeness. And in jazz theory, there are set structures for creating tension and building tension and then releasing this tension. So the idea of Troco is to use these structures, and they're encapsulated in something in the algorithm that we call the TRQ, or the tension and release quotient. So the TRQ is something that the user inputs at the beginning of generation, multiple TRQs over time, where lower values represent more release and higher values represent more tension. And each TRQ represents the change in tension or release of a given movement. And it's also important to note here that the tension release, the TRQ is not an absolute value, it's a relative value. So for instance, if we have one movement has a TRQ of -5, which is mildly released, if the subsequent TRQ is -1, it's still getting more released. It's just a lesser degree of release. And in the calculation of the TRQ, the considerations can more or less be split into two different categories. We have vertical tension, which relies on only elements at the present moment in time. And then we also have horizontal tension, which relies on context and elements present at a different time to infer the current amount of tension or release imparted by a movement. So I'm going to play an example for you. So as you can hear in this example, we have a sequence of C chords based on C. We have a C major chord, a C sus4 chord, a C7 sus4 chord, and a C7 sharp 5 chord. So as in this progression of chords, we can see it getting more tense. And the reason for a lot of this increase in tension can be viewed attributed to vertical tension. So in Troco, the considerations for creating vertical tension are the chord quality, which also factors into chromaticism within the chord itself through extensions and alterations. So an extension is if you continue building a chord. So for instance, if you have a C 11th chord, it not only contains C, E, and G, but it also contains the 7th B flat and the 9th D and the 11th F. You can also have alterations. So for instance, in the last chord in this sequence, we have a C7 sharp 5, which has the sharp 5th chromatic alteration, which increases tension in this case. We have the root being in or out of the key, and then we also have chord tones being out of the key. And then I'm going to shift over to horizontal tension. I'm going to play another. Yes?
This is the chair, Bob. Can you share your audio?
Oh, I'm sorry. I am not sure how to.
You have to stop sharing your screen and then ask to share again. Yeah.
It's giving me many issues. It's asking to restart audio devices. So it's currently not letting. I think I can continue without the examples, if that's okay.
That's fine, but we do have time allotted for technical issues.
Okay. I think in the meantime, I will continue without the examples. I'll still discuss the example just without the audio. So in this case, we have a C major chord, an A7 chord, an A flat 7 chord, and a B major chord. So this is an example of increasing degrees of tension, mostly attributed to horizontal tension. So one example, we can kind of see that the fact that this is due to horizontal tension rather than vertical tension is the fact that the last chord's quality is the same quality as the first chord. However, because of the context, it would be perceived as much more tense than the initial C major. So in troco, the considerations that factor into horizontal tension are the root note interval, notes in common with the previous chord, notes a half step away from the previous chord, which would be referred to as leading tones, and then the chord quality of the previous chord in relation to the current chord. And this last point is often used in jazz to build tension via parallel movement, in which a series of chords quality is the same, but by moving the root, we can build tension. So I'm just going to step through a few examples of how the TRQ might be calculated for a few chord sequences. So for example, we have this movement of C major to A minor. It's a diatonic movement. We have the relatively mild root note interval of a major sixth, and we share in common two chord tones of C major. So it's not a big change, and we end up with a TRQ of -2, which is mild release. In contrast, we have a C major to an A7 flat 5 chord, which still has the same root note interval. So we still have the same change from some sort of C chord to some sort of A chord, but now that A chord is a dominant chord with a chromatic alteration of the flat 5 and two chord tones that are not in the key of C major, resulting in a more tense TRQ of 4. And once we have this idea of the TRQ set up, we can transition to the general form of the algorithm itself. Here's very basic pseudocode, just outlining the general idea of the algorithm, but basically it's a best fit model. Before generation, the user inputs in a contour of desired TRQ values, the desired tension or release for each change in chord over time. And we also need to define a domain of possible chords that can be generated. This is made by defining possible domain of root notes and a possible domain of chord qualities. And then it's simply a best fit model of whichever chord from the options best matches the desired change in tension or release. And also at the bottom here of the pseudocode, we can see the calculation of the TRQ, which is simply each consideration adding or subtracting tension or release from the value. And in the actual specific calculation of the TRQ, I think it's important to address that there's no right answer. Just like there's no right music theory, there's no right way to specifically weight the tension and release quotient. And by altering the weighting of considerations and what is considered, we can get stylistically different generations, as different improvisers or different composers might favor different methods of creating release or creating tension and then subsequently releasing it. Also, there are different levels of interaction that a user could have with the algorithm. Without any musical knowledge, this idea of tension and release, I think, is somewhat universal. So anyone, even with no musical knowledge, could just input in a tension or release contour, and the chord domain would be predefined. So they could interact with the algorithm on that kind of top level, but someone with more knowledge of music might want to have control of the chord domain or even the weighting of the tension and release quotient in order to pinpoint the exact stylistic content that they might be looking for. So Troco was used in a simple demonstration video. It's kind of like a game-like environment that models a very simple narrative arc. So a user has control of a character in a three-dimensional environment in which they pass by a skull, which represents conflict and tension. And then after passing the skull, they make their way to a treasure chest, which represents victory or release. And the desired tension and release quotient is calculated by the player's relative distance to the skull compared to the treasure chest, with the skull increasing the TRQ and the treasure chest decreasing the TRQ. So before I play the video, which I'm now realizing I may have to figure out the audio situation for, I would like to just step through kind of how the system ended up generating the music it generated. So on the right here, we have the target TRQs that were calculated by the player's relative distances to the skull and the treasure chest. We see that it increases up to 10 and then decreases all the way down to -10. And then on the right, we have the chords. After these target TRQs were inputted into Troco, we have the chords that it generated. So the domain of chord choices in this example, the chord roots were just the C major scale, and the chord domain was major sixth, major seventh, and then minor seventh, minor ninth, and minor major seventh chords. And the chords, after being generated, were simply fed into an arpeggiator, which triggered samples that can be heard in the game. A few notes on the chords that were generated. Generally, we can see that this is, very superficial analysis, if you will, but generally the chords got more dissonant near the skull. We had more unexpected odd root note movements near the skull. And then as we get to lower TRQ values, we see that the progression actually resolved via a 2-5-1 progression, which is a very common cadence used in jazz music at the end of a progression or at the end of a section. So now I have the example, and I'm going to attempt to re-share my screen with audio at this point. Okay, so hopefully this audio is enabled. If someone could just tell me if this is working. Is it audible?
No.
Right, sorry, just one moment.
Do you have the video separate? It's just not embedded. It might just play.
Yeah, let me try that. I was told to also restart my browser, so I just did that.
While you're sorting that out, can I just I meant to remind everybody, if you have questions for Matthew, can you put them into the Slack channel? I'm monitoring the Slack channel for questions. Thank you.
I've got Matthew's video queued up to play this video, the sound. If I want to, I can share my screen.
I think I have it working. If this last try doesn't work, I think that'd be great. All right. Third time's the charm, hopefully. Does it work?
Yes.
Yay. All right. So here's the demonstration of the video that was stepped through in the example. Yeah. And then a few next steps for where Troco might go in the future. I think it could be really rewarding to analyze the work of composers and improvisers within the tension and release quotient framework to inform its design. As mentioned earlier, the weighting of the weighting of considerations in the tension release quotient and the considerations themselves can have a big impact on the stylistic content of the generations. So fine-tuning the tension and release quotient and or allowing more choice in the tension and release quotient could greatly expand the range of possible generations. And then also applying the Troco's general structure and the general TRQ structure to melody, which is somewhat of a tall order. I think mostly because not only would, if we have melody and chords being generated, not only would the tension and release imparted by a specific chord need to be considered, but also the tension and release imparted by the coexistence of a melody note and a chord. But I think the same general structure of the TRQ could still be easily extrapolated to melody or even perhaps rhythm. And then finally, testing possible implementations, possibly using some sort of sentiment analysis, even a musical accompaniment to some sort of social media feed or some sort of text feed, an audiobook perhaps, as well as just other games or environments. Thank you. So I believe it's time for questions.
Great, thank you, Matthew. Apologies for the name mix-up again as well. So we have a couple of minutes for some quick questions. If anyone, I'm just checking the Slack. I've got a couple of questions anyway. Sorry, yeah, I had a quick question in regards to, you were mentioning horizontal and vertical, the tension horizontal and vertically, and possibly I just looked away for a moment. How are they combined, or do you do them individually, like you get, oh, sorry, I should be speaking to you. Do you do like all the vertical and all the horizontal, or is it just one by one, or what is there a weighting towards horizontal versus vertical tension?
Yeah, so there's definitely weightings within horizontal and vertical tension, but each consideration simply increases or decreases the overall TRQ of a movement. It's more that the considerations can be categorized in one of the two as either a horizontal consideration or a vertical consideration. They're not, the grouping of them does not affect the calculation itself.
Okay, sure, I understand. And could you tell me a little bit about the initialization as well? How does the user initialize the process? Like, is that all decided beforehand? Like from where they start?
So one thing about the TRQ representing a change is that an initial state is needed. So currently the user specifies what the initial chord would be, and the user specifies what the initial chord would be, and then subsequent chords are calculated based on that chord. But another possibility is that this is not how it currently functions, but another possibility is that only vertical considerations could be used to generate the first chord, because all of these considerations would still be relevant to the overall tension.
Okay, great. Sorry, the questions are suddenly exploding in the last 2 minutes, literally. So let's see if I can pick the first one. How can you consider moment-to-moment tension release as in the demo with larger scale duration, for example, 2 minutes or 5 minutes? Yeah, so how would you consider the tension as it evolved more over time?
Right, so currently it's the only, currently it's the tension is only considered relative to the last state, which is still creating effective generations, but is somewhat dangerous, actually. So in the future, something that would definitely be worked on is making the algorithm knowledgeable of past steps. Especially, I think this would be extremely important when we have ascending or descending figures, because only by looking at the last state, we would have no knowledge of any sort of movement like this. So currently, it's only, the algorithm is only aware of however long it has been since the last state change.
Okay, great. There was, yeah, there's quite a few questions here. I'm just trying to pick a relatively quick one. Have you tried connecting the concept of tension and release to aspects other than dissonance, such as rhythm or texture?
I have not, but it's definitely in the works.
Yeah, I'd imagine so. In the view of time, I think we'll have to move on without addressing all of the questions, but I would encourage you to go in and have a look at them, because some people have written some very detailed questions there, and I'm sure you could respond to them in your own time if you have time later on.
Definitely happy to respond in Slack.
Perfect. Great. Okay, and thank you for those questions.
Thank
you, Matthew. Okay, so next up we have Jean-Francois Charles. I'm hoping I wrote your name down correctly. And Jean-Francois is going to speak on sonic print timbre classification with live training for musical applications. Thank you.
Hello. Thank you for listening. I'm Jean-François Charles, and I'm presenting on behalf of the team that we formed with composers Gil Dory and Joseph Norman. This project started a long time ago when I was studying electronic music with Hans Tuchko in France. One day, he demonstrated for the class a neural network object. It would potentially operate live classification of different vocalic sounds. At the time, this object didn't include the training algorithm, so we couldn't really use it. But it opened a great discussion among the students. Just imagine the possibilities. When a singer sings with different timbres, we would automatically route the sound to different effects. For instance, we would apply distortion to spoken voice and a long reverberation to sung vowels. And maybe when the singer whispers, we could trigger a specific sequence of sound files. So that was the impulse that led us to create the Sonic Print tool and to evaluate its use in new musical compositions. In the field of machine learning applied to music performance, a significant body of work has been published with the goal of mapping either physical gesture or audio features to sound processing. Examples include the M&M Toolbox, the Wakinator application, the Timbre ID Pure Data Object, or the SEC Toolbox. And artists have used these tools to create new music and interactive art. While these tools are highly customizable and flexible, they present a steep learning curve to musicians with no knowledge of machine learning concepts and algorithms. Our goal with Sonic Print is to provide a tool seamlessly integrated in an artist's work environment, offering not only a fast live analysis, but also live learning. Before we show an example, let's clarify how we use the term timbre. We apply the word timbre to classes going beyond the case of musical instruments. For instance, we may contrast the timbre of a flute playing with a normal mode versus flutter tongue, or the timbre of different consonants like s, sh, or th. Now, let's have a look at Sonic Print in action as a Max for Live device. Oops. In this second example, the sound is routed to 4 different tracks depending on the live classification. Now that we have a better feel for this tool, let's have a look behind the scenes. We're working in a context of supervised learning. Many options are available when it comes to the choice of audio features and learning algorithm. Let's start with the audio features. A common set of features are the Mel frequency capture coefficients, MFCC. They've been widely used for speech processing because they are especially pertinent to separate source and filter when a source filter model applies. Here, though, we cannot assume that a source filter model would apply to our input sounds. So we decide to use directly the instantaneous spectral repetition of energy. And rather than using the melody-oriented MEL scale, we use the more general BARC scale. For the learning algorithm, we could use a general K nearest neighbors, but we're interested in neural networks for the speed they can achieve in live classification. And when it comes to neural networks, we first need to wonder if a linear model could apply. It's an important step, and to illustrate that, let's have a look at the Sonar Signals Benchmark. This data set comes from the spectral analysis of sonar responses in presence of either metal cylinders or cylindrically shaped rocks. It's been widely used to test learning algorithms. And although it's been used since 1988, it was only shown in 1998 that the full set of 208 points was linearly separable. It is indeed a well-known result that with a limited number of training points, the probability that data points be linearly separable is not negligible. And it increases when the input data are correlated. That is exactly the situation we are in. A musician will assign a single output, sound class, to a set of correlated input vectors, the BARC values representing correlated timbres. That's the reason why we're going to use a single layer perceptron, which is sufficient to model linear processes. Now, it's not guaranteed that our sets will be linearly separable. So instead of using a typical classification perceptron, which might not converge, we dispense with any sigmoid activation function. Our perceptron will be reduced to a multivariate linear interpolation algorithm. So this is the engine behind sonic print. Beyond guaranteed convergence, another important advantage of the linear regression is the very fast training algorithm. Moreover, we can easily compute the mean squared error from the error matrix in order to display a learning quality indicator to the user. The implementation in Max is simple. We use the built-in linear algebra functions. On this Max version of Sonic Print, you can see the bidimensional output Y estimate shown on a 4-quadrant square. The position in one of the quadrants determines the classification. On the Max for Live version, we show the recorded waveforms for convenience. But as we have seen, the processing is made on spectral data. At the bottom here, you can see on the left, the BARC reduced spectrum of the live input. And to the right of this indicator are 4 Bark-reduced spectrograms corresponding to the 4 sound classes. Once concatenated, they constitute the complete learning set. Sonic Print was made available to several artists over the last couple of years. We are presenting here 2 resulting works: Joseph Norman's Fracture Morphosis and Gildori's Siete Dolores. Fracture Morphosis is a composition for trombone, violin, and double bass with live electronics. Each musician performs with their instrument and a laptop processing their own sound. The output of the processing lines for each instrument is routed to a shared spatialization system. In Fracture Morphosis, each instrumentalist is provided with 4 distinct initial musical gestures. The learning step of Sonic Print is built into the piece as an introduction during which each instrument's gesture is performed without audio processing. You see here the double bass initial gestures. Sonic Print acts as a gate to route the musician's sound to one of 4 processing lines, depending on the resemblance of the live timbre to one of the 4 learned classes. The composer designed the live audio processes to give each of the 4 individual sounds a unique processed identity. After the introduction, the musical gestures are altered over the course of the piece so that the distinctions between them become more and more ambiguous. The sonic identity of the pairing between musical gesture and specific effect gradually dissolves. Although the performers received no training in machine learning concepts, they could use the system very quickly in rehearsal. For more about the piece, I invite you to listen to the recording. Siete Dolores results from the close collaboration between composer Gildori and saxophonist Jonathan Chazan. Together, they explore elements of a musical composition through the prism of timbre, with the prospective goal of developing a method for composers to indicate specific timbres and for performers to interpret them precisely. Chazan, an experienced performer of both early and contemporary music, observed that different music styles embed in their performance practice different sound production modes, each resulting in a slightly different timbre. Dori explores in Siete Dolores the transition between 7 such states. He separates timbre production from other elements of sound to reconstruct it in unexpected ways. Throughout the piece, motives morph through changes in timbral quality and slowly reveal more of themselves. On these score excerpts, we see an initial motive morphing over time. The circled digits indicate which sound production state, which timbre, the performer should use. The work uses Sonic Print to identify saxophone timbres and map them to LED lights inserted into a second saxophone placed on stage. The LED colors provide visual signals that aim to support guiding the audience through the timbral experience. We note that since there are 7 timbres to identify, the composer combined 2 Sonic Print units. To route the sounds to the first or second unit, Dori used another level of spectral analysis. Although he could adjust all parameters while working offline, the results were not accurate enough for subtle timbre changes in a live situation. So he used fixed cues in some parts. I invite you to listen to excerpts from a version of Siete Dolores with the included link. The limitations of this tool include the choice of 4 classes. Many spectral details are lost because we use just 24 filters. The output is undefined when the analyzed sound is far from any training example. The training set has no memory. We would need to modify the tool to make the history of learned samples contribute to the learning. Finally, The quiet parts in the training samples are not filtered out. The user has to make sure they don't include silence in different training examples, which would result in a more difficult discrimination. In conclusion, SonicPrint successfully allowed several composers and performers to use automatic timbre recognition and live learning in new musical creations. The tool is seamlessly integrated in environments widely used by creative musicians, Max and Max for Live. Finally, the use of a linear model applied to spectral data enables both a streamlined interface and a short, finite learning time. Thank you.
Great. Thank you, Jean-Francois. Looks like a really interesting system there. So once again, can everyone, if you have a question, pop it into the Slack channel. I'll keep an eye. I suppose I have a very general question to start off with. What did the performers think of using this system?
Yeah, so the well, the first participants were really the composers who learned how to play with it. And then in the case of Joseph Norman, for instance, he gave a patch to each of the three performers, and he just told them when to press when to press the learn button, and so they were just on board, just playing their part, basically like an orchestra musician would play their part.
Okay, so yeah, they just got on with the job.
Yeah,
I understand. I noticed that you had your performances were 2018 and 2019. Is that correct?
Yes.
So has this system changed much since then, or is this the same system now?
So actually, the initial performances were made with a Max version of the tool, and the composers did program completely things in Max. So what changed since then is that I optimized a version for Max for Live.
Okay.
That's the main thing that happened after the two presented works is the Max for Live version.
Okay, so that makes it much easier to use, I assume.
Live. Yeah. So in the Max version, if I can, maybe I should share my screen again. But in the Max version, we have access to more information. So, for instance, here I can actually, if I can just do it. So, yeah. So here on the left, you can see my spectrum. Yeah. Really, you can see the Bach reduced spectrum live. You can see the spectrograms. And in the middle, I have this, okay, let me stop the analysis. But basically in the middle, it's the output. It's the two-dimension output of the linear interpolation that is just shown. So it really shows you where the interpolation is going, the regression. So it explains more. And in the Max for Live, actually, the job was more to choose what to show and what not to show. Actually, the waveforms, for instance, in the initial version of the work, I didn't show the waveform. I just showed the spectrograms. But as a Max for Live tool, I decided to make it more convenient for most users to not even show the spectrogram. So I actually don't show the spectrogram in the Max for Live version. It's inside the patch, of course, but it's not shown.
Okay, great. Sorry, just one other small question. I just didn't pick up on what the instrumentation for the second example you were talking about, Gil. What instrument?
Yeah. So the second example was is a piece. So the second example is a piece for saxophone and multimedia. Actually, Gil Dory he took the tool. He worked with the saxophonist, and they really went about exploration. So it's like a work and the concept of the work at the same time. So they performed several versions of their own creations. One version was for actually saxophone and live electronics. And then he decided to make it solo saxophone and to make no electronic sounds, to just have the acoustic saxophone and to have live electronics just drive either LED lights, as I showed today, or like live visuals and like video processing. And he as a creator, as an artist, he found it was even more interesting for the audience to listen to the timbre and to have that visual feedback helping be in that world of timbre, rather than having electronic music at the same time, which was the case in the first versions.
Okay, perfect. I know you shared the links to the demos. They're in, I know they're in the presentation, they're probably in the paper as well. If you have them handy, maybe throw them into the Slack channel as well, and people could just have a little look straight afterwards.
I will link the two works as soon as we're done.
Yeah. That would be great. So I don't see any other questions just coming in at the moment. The great thing about Slack as a tool is, I mean, everyone should feel free to ask questions later on when we think of them, as you would if we were having coffee straight after this session, you know. So please do stay on to the Slack channels, and I'd encourage particularly all our presenters today to check in on it today and even tomorrow, and just check to see if there's any questions there for you. So thank you, Jean-Francois.
Thank you.
That person. Great. So we'll move on to our third speaker today, who is Jeff Enns. Is that correct? And Jeff will be presenting on improved listening experiment design for generative systems. So we have.
Hello, everyone. So I'm Jeff, and I'm going to discuss some research on listening experiment design for generative systems that I worked on with Philippe. So in recent years, there's been a lot of interesting and exciting work involving generative systems. For the most part, in order to benchmark these systems, we rely on listening experiments. However, there are significant discrepancies between studies with respect to experimental design. In this presentation, we discuss recommendations for improvement backed by some experimental evidence. So let's start with an overview of experimental design. In the simplest sense, a listening experiment is comprised of three components: participants, shown in red, questions, shown in blue, and responses, shown in green. In our context, a question is typically a set of one or more musical examples, which a participant must listen to before providing some sort of response. Depending on the methodology employed, participants may be asked to provide a variety of responses, ranging from predictions on whether a musical example was generated or human composed, to qualitative feedback on various aspects of the musical examples. Of course, to get meaningful results, we must collect more than one response. In this experiment, we have two participants, P0 and P1, and three questions, Q0, Q1, and Q2. And then four responses shown in green are collected. In our study, we're going to investigate the role of two hyperparameters of experimental design: the proportion of participants, which is simply the total number of participants divided by the total number of responses collected. So in this case, that's 0.5. And the proportion of questions, which is the total number of questions divided by the total number of responses collected. So when we design an experiment, we aim to investigate the relationship between multiple factors. And there are two types of factors: fixed and random factors. A fixed factor has a fixed number of levels that are of interest to the researcher. One common example in this context is the system factor, as there'll be a fixed number of systems being compared in an experiment. So here we have two systems, M0 and M1, and that would be our fixed factor. The other type of factor is a random factor, where only a random subset of the large number of possible levels, all of which are of interest to the researcher, can be feasibly included in the experiment. For example, participants are a random factor, as there's a large group of possible participants we would be interested in including in our experiment. However, we have to settle for a much smaller subset. In the context of a listening experiment, questions are another random factor, since generative systems can continually produce new musical samples, but we can only feasibly include a random subset. Once the factors have been established, it's necessary to determine the experiment design, which specifies the relationship between factors. Pairs of factors can be crossed or nested. In a cross design, shown above, each participant is exposed to each of the questions so that every possible combination of participant and question is included in the experiment. As you can see here, P0 and P1 are both exposed to Q0 and Q1. In a nested question design, each level of a factor co-occurs with only one level of the other. So here, the question factor is nested within the participant factor so that each participant is exposed to different questions. As a result, each question is only used once, and we have 4 unique questions being employed here, as opposed to in cross-question design where we only have 2. It is also possible to have a partially crossed design. Here, the participant factor is partially crossed with the question factor, as different participants are occasionally exposed to the same question. You can see that P0 and P1 are both exposed to Q0, but Q1 and Q2 are only used once in the experiment. So the main difference between these 3 designs is the proportion of participants. In a nested question design, the proportion of questions is always 1, while in a partially crossed and fully crossed designs, they feature a lower proportion of questions. Sorry, I meant to say the main difference between these designs is the proportion of questions. Now that we have a good understanding of what a listening experiment is and some of the different designs that can be employed, we'll touch on the motivating factors behind this research. First of all, when we make poor choices with regards to experimental design, in the worst case, our results may be invalid. And at best, these poor choices will reduce the reliability of the experimental results. Secondly, since conducting a listening experiment requires an investment of both time and money, it is in the researcher's best interest to make efficient use of allocated resources. Finally, and probably most importantly, an overview of recently published listen studies reveals large discrepancies with respect to experimental design. And this indicates that there's not yet a consensus on how to design a listening experiment. Here we plot the experimental design of recent studies. It's immediately evident that there's a lot of variance in terms of the number of questions featured in each experiment, shown on the y-axis. In addition, there are a variety of experimental designs employed, including partially crossed, crossed, and nested designs, which are notated using the triangle, cross, and circle symbols in the plot. This naturally leads to the question, do these variations in experimental design have a significant impact? To answer these questions, or answer this question, we conduct 2 experiments. In the first experiment, we calculate the power for nested question and crossed question designs. In the plots, the contour lines and shade indicate the power of an experiment parameterized by the number of participants and the number of questions per participant. As a result, we can directly compare the power of a nested question and crossed question design given the same amount of resources. The results demonstrate that nested question designs are uniformly more powerful than cross question designs. In fact, we found that nested questions were 2.3 times more powerful than cross question designs on average. If we take a look at the cross question plot, we can see that in some cases there's barely any advantage to adding additional participants. This is mainly due to the fact that adding additional participants only increases the number of participants, not the number of questions, as each participant is exposed to the same set of questions in a cross design. In contrast, with the nested question design, we always see increases in power when a new participant is added. This is because adding a new participant also means that the number of questions is being increased as each participant is exposed to a unique set of questions in a nested design. The difference between these 2 plots clearly demonstrates that the proportion of questions is important as cross designs, which have a small proportion of questions, are uniformly less powerful than nested designs, which will always have a proportion of questions of 1, as each question is unique. We can plot a line which shows how the power varies when the proportion of participants is manipulated while holding the total number of responses and proportion of questions constant. This is shown as the dotted line here that kind of curves across the plot. And if we plot a whole bunch of them, all with different numbers of total number of responses, we see that in all cases, power increases as the proportion of participants is increased. In the second experiment, we calculate the variance of experimental results using different experiment designs. To do this, we start with the raw data collected in an actual listening study. Then we randomly sample a subset of the responses such that our chosen experimental design is satisfied. For example, if we are measuring the variance of a cross design with 4 participants, 2 questions, and 8 responses, we need to ensure that the subset we randomly selected satisfies these conditions. Then we calculate the average response. And this process is repeated 50,000 times to produce a distribution of average responses corresponding to a particular experiment design. To compare 2 experiment designs, we simply compute this distribution for each experimental design using the same original raw data, and then use Levine's test to compare the variance. We repeat this entire procedure 100 times and report the number of times that there was a significant difference in variance. So using the results collected in the Loch Ness listening study, we can compare 2 nested question designs, one with a smaller proportion of participants. And we found, unsurprisingly, that the experimental design with a larger proportion of participants had significantly less variance in 100% of the trials. Using the same approach, we collect or use data from the BachBot listening study, and we compare a partially crossed design with a small proportion of questions and a nested question design with a portion of questions of 1. Once again, we find that the experiment design with a larger proportion of questions has significantly less variance in 100% of the trials. Finally, using data that was collected in Collins' listening study, we compare a cross design with a small proportion of participants and a partially crossed design. Here we found that the experimental design with the larger proportion of participants had significantly less variance in 95% of the trials. Collectively, the results of both experiments demonstrate that the proportion of questions and the proportion of participants should be maximized, as decreasing either proportion decreases power and increases inter-experiment variance. However, the ideal experimental design must also take other factors into consideration. In particular, we must consider the endpoint of the experiment when designing the experiment. Consider 2 hypothetical experiments. In experiment A, we want to measure the valence of audio clips. And in experiment B, we want to compare system A and B. Note that experiment B is a prototypical example of a listening study. In experiment A, the endpoint of the experiment is an average valence per audio clip. While on the other hand, in experiment B, the endpoint of the experiment is not the average rating per clip, as we do not care how a particular clip is rated. Rather, we care how a particular system is rated. In both cases, we want to maximize the reliability of our endpoint. In experiment A, this means we want to maximize the number of questions per audio clip, while in experiment B, this means we want to maximize the number of questions per system. Admittedly, if the endpoint of your experiment includes or is primarily focused on measuring inter-rater agreement, then you need to use repeated questions. However, in most cases, this is not the purpose of listening studies that evaluate generative systems. So to close, I will offer some recommendations for listening experiment design. Now, hopefully it goes without saying that increasing the number of responses is always beneficial. However, these recommendations are based on the assumption that resources are finite. as researchers have budgets, both monetary and temporal, that are going to place inherent restrictions on the number of responses that can be collected. So first, we must ensure that the proportion of questions is as large as possible. Practically, this is going to mean avoiding crossed question designs, only using partially crossed designs when they feature a large proportion of questions, and in most cases, favoring nested question designs, which are going to maximize the proportion of questions. If we return to the plot of experimental designs that we reviewed earlier, we can see that many experiments could be improved by simply increasing the proportion of questions, shown here with the red arrows, while holding all other factors constant. And this is a very low-cost fix, as it would simply involve taking more samples from the generative systems being tested, and including them in the experiment. So it's very cheap. Secondly, as much as possible, ensure that the proportion of participants is large. So on a whole, researchers seem to be fairly sensitive to the participant factor, but it's also worth noting that limits should be placed on the total number of responses collected per participant. According to experimental results that we presented here, an ideal experiment would actually feature one response per participant. However, this is rarely feasible in practice, since there are costs associated with acquiring each additional participant. All that being said, if you only remember one thing from this presentation, it's that increasing the number of questions, and in other words, the number of generated samples in a listening study, is a cheap and easy way to improve experimental reliability and power. Thank you.
Excellent. Thank you, Jeff. So I suppose, yeah, it's something that we all love to hate, isn't it? Evaluation. It all comes down to evaluation and listening experience. And you've raised a very good point, I think, in that it's not just about doing evaluation, but it's about doing the best or the optimum evaluation that you can do when it comes to actually, our listening test should not be something we tack on at the end just to keep an external examiner happy. It is a very, very important aspect of research, and it's not simple, as you've just pointed out. So I have a question here from Bob saying, nice analysis. What happens when the question is something like, is this good music or is this composed by an AI? In other words, the statistical validity of an experiment means little when the construct of one is measuring is not what is desired.
Sure. So, I mean, if I'm understanding your question correctly, it doesn't in particular matter if the question is this good music or is this composed by AI, whatever question you want to be asking. The point here is that often when you're designing an experiment, you focus on increasing the sample size of participants. We all know we're not going to make an experiment with just 2 participants. We want to increase that sample size. But we also have to think about the sample size of generated samples, because that's another random factor in our designs. And all too often, we don't increase that sample size sufficiently, or think just about, we can get 6 samples and that's enough. So it doesn't, in my view, really depend too much on the question you're asking. It's just a general recommendation, because it's very cheap and very simple to generate samples. Why not increase those to using as many samples as we can, so we get an accurate representation of what the system is capable of? I hope that answers your question.
Okay, Bob, feel free to, I'm monitoring here, so feel free to come back. I've got a question from Robin as well. What about the expertise of the listeners? So yeah, I think that's a good question. Do you want to give the people with more expertise the more important questions, or more questions, or what way do you look at it that way?
Well, I mean, if you're concerned with the expertise of the listeners, then, I mean, you can screen them however you would like. I'm really just talking about the sample sizes, because that's the important thing. And the big thing I noticed in the literature is sometimes they do a study and they'd take a generative system and they'd only use 10 samples from that generative system. And it's like, if I were trying to evaluate, someone's ability, and I only asked them 10 questions, and that's what I gave to all my participants to evaluate that person, it wouldn't work very well. So the expertise of listeners is certainly important, but I think most people are aware of that already. And that's why you'll have, they may separate the results based on novices or advanced people with music expertise. So the focus here is mainly just, we need to focus on a number of samples that are being evaluated from a particular system, because often that is too small and it's a cheap and easy fix to increase reliability.
Okay, Robin has come back with a comment again, so I'll just stick with him for the moment. It says, use of consensual assessment techniques suggests a small number of experts is preferred.
Yeah, I mean, I would disagree with that in the sense of what you need to get an accurate result. The more, I guess the idea there is that you're trying to kind of converge to a single assessment. But I mean, statistically, the results that we observed is that this increasing the sample size for participants or for questions increases the power and reduces inter-experiment variance.
I suppose it depends on what you're asking as well. If you're just doing a general,
sure,
if the questions don't require expertise, then it shouldn't matter too much.
Sure, exactly. And that's what I kind of tried to touch on, towards the end of the presentation. It really does depend on what your goal is. But I see a lot of papers with just the goal to say, system A is better than the corpus or just better than system B. And if that's all you're doing and you're not asking more complicated questions and you don't have sufficient sample size, I mean, there's an easy improvement right there.
Okay. There's another question here. If all participants answer one question, how do you make sure all the questions are answered and you have enough response for each question answered? So
I'm not sure I understand.
If all participants answer one question, how to make sure all questions are answered and you have enough response for each question answered. So I suppose, is it that, do you need a certain amount of responses to any given question? I think it's
well, my point here would be that in most cases you really don't, unless you're concerned with inter-rater agreement, which was kind of the whole point of the example between measuring the valence of audio clips, where your endpoint is you want an accurate measurement for each audio clip, if you're measuring a system, you want an accurate measurement for the system, and you don't really care how accurately each audio clip is, because the cumulative accuracy of having many responses distributed amongst many questions will be represented based on the system.
Okay. So did you say at one point that the ideal is that one person per question?
Yeah, that would be, statistically, that is the ideal, unless of course you're actually interested in doing some sort of study on inter-rater agreement. I mean, unless that's actually part of your results, but most of the time it isn't. Most of the time, the simple question, right, is system A better than system B?
Mm-hmm. Yeah.
And in that case, you have to maximize the amount of examples that are coming from each system, because otherwise there's the risk of misrepresenting them.
Yeah. Robin's come back and said again that one of the papers you surveyed uses an adaptation of CAT, which is the consensual assessment technique. So I guess that's something, again, to inter-rater agreement is crucial if using CAT. Yeah. So it seems like there might be a conversation there you could have definitely offline. Yeah. Sorry. Could I ask, I had bot written down here. It was one that, it grabbed my attention on one of your graphs that had so many participants, I think, but had very few questions. What exactly was that, the bot?
So it's a study on a system that generates Bach-Chorales. And yes, it did have, I think it has the most participants of any recent listen study. It was somewhere, somewhere around, I don't know, maybe 2,000 or something. So a whole lot. And it actually only featured 12 or so unique questions. So if you think about it, a system's capable of generating millions of samples. And what if we picked 12 really, like, what if we just got unlucky and the 12 we picked were not so great?
Mm-hmm.
Like, that's totally could happen. And so it just makes sense that, why not? If you're collecting so many responses, you really should increase the number of samples. And I think perhaps in that case, the authors may not have known preemptively that they were going to get so many results. I wouldn't have expected that, because it kind of, that's more than a lot of studies get. And they just kind of crowdsourced it online. They got people to come to the link and participate. So I can understand kind of why maybe they didn't think of that beforehand. So that's why I'm kind of trying to talk about it now, because it's something you need to consider up front. Try to maximize it, because there's really no disadvantages unless you have some specific other questions that you're trying to answer.
Yeah, I agree. I think it's a lot to do with planning and knowing what you want to get out of your experiments. I'll take a final question from Oded. Is the quality of system A and B reduced to their outputs? Aren't we also considering how things are achieved, the process, not just the output?
Sure. I totally agree that those types of things should be considered. It's just in a lot of these studies, and that's the main focus of the paper, is just to critique these types of studies and those particular methodologies. They're just focusing on the outputs, and that's the kind of methodology that those experiments are based on. I don't necessarily think that's the only valid or should be the only way of evaluating a system. I totally agree with that.
Okay, great. Yeah, there's a few chats. You might want to pop into the chat channel yourself then, in case I didn't. The Slack channel yourself. There's some questions there, so it's always good to get another person's point of view.
For sure.
Fantastic. I think the take home is we have to think very, very carefully about our listening experiments. Definitely, there's a lot to be said for them. So thank you very much, Jeff. So we can move on to our final presenter today. Joachim, who joined us there, I think.
Hello, yeah.
Hi, Joachim, how are you?
Hi.
Joachim, is this? I'm sorry, I'm not doing great with names today.
That's okay, no problem.
So, sorry, just to check, you've got the presentation ready to go, or did you want to play the video?
I think it would be better to play the video because of the route. I'm using a DAW software that needs special routing, and I don't know how to route it to Zoom.
Yep, that's no problem.
I think it would be better if we watch the video, and I will be able to answer any questions.
You come back to questions, yeah, that's no problem. Bob, do you happen to have that one lined up?
Yes, 1 second.
Yeah, no problem. And for anyone who doesn't realize that Bob very much likes his gorgeous little doggy, so much so that there is a whole Slack channel dedicated to, oh, where's it gone now? There is a pet parade in Slack. So I would encourage anyone who has their nice dogs and cats around for the weekend to take them over there as well.
Okay, here it comes.
Fantastic.
Uh-oh. 1 second.
Yeah, no problem. I already saw a question come in for you earlier on, Joachim. So if anyone else has questions, just pop them up in Slack. I'll keep an eye.
Okay, I have to end this streaming service and then start the next stream.
Hello, my name is Joaquin Jimenez, and I would like to talk to you about how I am using machine learning to perform in the way a dub music producer performs. This idea started after learning how these producers historically have taken advantage of technologies and have given so much to audio engineering and recording. In dub music, the producer uses the mixing console as an instrument for encouraging musical intervention, the mixer parameters. One of the most recurring techniques includes isolating tracks, manipulating the volume faders, and send controls. This way, emphasizing some parts of the track, creating space via time effects such as delay and reverb. I can continue this idea using machine learning, or I can play the
We're going back. Let's see if we're back now. 1 second. Okay, sorry everybody. We're going to try this another way. We're going to play through Roshane's video.
Okay. Just let me know if this is playing.
It's playing.
Cool.
Hello, my name is Joaquin Jimenez, and I would like to talk to you about how I am using machine learning to perform in the way a dub music producer performs. This idea started after learning how these producers historically have taken advantage of technologies and have given so much to audio engineering and recording. In dub music, the producer uses the mixing console as an instrument for encouraging musical intervention and to create instead of fine-tuning the mixer parameters. One of the most recurring techniques includes isolating tracks, manipulating the volume faders, and send controls. This way, emphasizing some parts of the track, creating space via time effects such as delay and reverb. I can continue this idea using machine learning, and that's why I created this assistant to help me while I perform. The idea of this project is not to create an autonomous system that performs by itself. I am just looking for an assistant that works with me, and I am not intending to predict the best solution or the optimal solution. In this session, I will show you the interface implementation, design, and machine learning model. Also, I will talk a little bit about the creation of the dataset.
Just something went on with the audio on that. Don't know what happened there.
Yes, sorry about that. I didn't realize it sounded okay on my end.
We have shared the video on, oh, you're on mute, sorry. We've shared the video on Slack.
I can explain what was going on there.
Yeah.
I was not actually speaking in that part. I wanted to let the music play, and I was explaining the reasoning, the interface, definition, and I was about to explain how the same interface allows you to enter more data. So if I may share my screen now, if so to continue the explanation or
Yes, that's fine.
yeah, okay. So this is the it's I'm using Ableton. Can you see my screen now?
Yes.
Okay. I don't know if I'll be able to share the audio because it needs a special routing, which I'm trying here. Just let me know if you can hear this.
No.
No? Well, it's okay. We can just see what's going on here. I have this project started with my fascination of dub music and how dub producers' techniques have extended to other areas of production and recording. And what I was trying to do here is the producers do. You just saw the video of producers using the mixer as an instrument to perform or to create a new version of a recorded piece. I want to perform my own music here in Ableton Live. That's what this DAW does, because it's made to perform live. But I want an intelligent assistant to act like a dub producer making a dub version of my music. So I made this assistant. It contains a machine learning model which implements a neural network to classify the position of these knobs right here, which for me are semantic controls. I just express the way I want the mix to happen, and the device sets the whole mixer to express this semantic setting. I don't know how to call it properly. You can see that this device actually shows the position of the. Let me run it because it needs to run in order to work. There we go. So these bars right here represent the volume faders of these channels. It's kind of difficult to see, but that's why I made this interface. It's showing the position of the faders to work the same way as you just saw in the videos. And I think it's important to mention that these channels right here in the middle represent harmonic or melodic sounds. The others at the extremes are percussive sounds. And let's say I train my model. I will talk about my model in a few minutes. I train my model to express color. Let's say I want to, for me, color is the amount of harmonic or melodic content. If I want more melodic content, I let the model do this. You can see that it puts more emphasis on the central channels. If I want more rhythm, for example, now it's emphasizing the channels to the sides, to the left and to the right. And also how dynamic it is. You saw in the videos that they were sometimes moving controls very fast or sometimes very slow, depending on what they were trying to express. In the end, I wanted to have a reduced amount of controls to control the whole mix. And this is also a reduced version because I am controlling 24 parameters or mapping 24 parameters to these 3 semantic controls. You will see in the video how this sounds, but this has proven to be expressive, and it really does work as an assistant. To train this model, I can set the data here. These values doesn't exactly represent the position of the mixer controls because the mixer controls are dynamic. I'm just setting, for example, in the middle window, how probable it is to have a slider to be up or down. In the next window to the right, I can set how dynamic, how often it moves. And these are special controls for sending the channels audio to each delay effect. And what I do after setting these levels is to classify how would I think the semantic controls represent this behavior. Let's say we have a little bit of color, I would say in the middle, it's highly dynamic. Let me reduce the emphasis on the rhythmical content so I can classify it like this. And I just pressed learn this. You will see that the number went up one. It was 152. And I can retrain my model. I can do this even during performance. I can do it many times if I want because the model takes a random subset of the data set. This is interesting, but I don't know if I would. This is an ongoing project. It's not finished. I need to test other models, but so far I think it does a pretty good job. I don't know how to make you hear this. I don't know if you are able to hear it right now because I can't.
No, we can't at the moment, Joachim, I'm sorry. But the video is in the Slack channel now at the moment for anyone, when we are using the Slack channel quite well, so people can check it out and can get back to you. But could I, there was actually a question from somebody earlier on who read your paper. So if I could just address this one to you now before we finish up. So from Jason saying, your paper describes a Max for Live device using machine learning that learns a mapping from 3 semantic controls to 24 mixer sliders and mentions achieving satisfactory results with 100 or more rows of training data, which is remarkable. I'm wondering how you train it and whether the audio equivalent of labeling is involved. Do you generate your training in reverse, your training data in reverse, so to speak? For example, do you set the position of these 24 sliders, listen to the quality of the dub mix, and then somehow create the data? Is that the way you do it?
Yeah, Oh, sorry. That's something I would like to do. It's not possible for me to set the position of my controls and save it because the Ableton Live API works from Max to Ableton Live, not the other way. Max cannot read the position of my controls. I will need to implement absolute control from the Max patch. Yes, but that's a good question. I would like to hear, set a current state of the mixer and say, I like this. save it or add it to the training dataset.
Great. Yeah. And you use this live yourself, do you?
Not anymore. I wanted to leave that to the patch, because what I'm doing is to perform. I am taking care of the music. I am playing notes, moving oscillators, controlling the instruments.
Great. Okay. Thank you very much, Joachim. I'm sorry about the technical difficulty we had there. I'm very conscious that there's another session starting on the hour. So to give everyone time to run and grab a glass of water or do whatever it is you need to do, whatever time of day it is in your time frame or time zone. I just want to thank all of the speakers who joined us today. Thank you, Bob, for keeping things running, ticking over. It's the first session, so I'm sure we'll have ironed out everything by the morning. And yeah, I'd encourage everyone to keep chatting in the Slack channel if you have more questions for our speakers. There's links there as well for demos and for demos and various things that came up during the session. So thank you, everyone. And I don't know if you want to say a few words.
Thank you, Roshane.
Thank you.
See you in 10 minutes.
Great. Okay. Thank you all.